Hi, my name is Ron Demko. I'm an engineer at Kyocera AVX, and today I'd like to talk about supercapacitors used in powering IoT modules and low power electronics. Our talk is built upon the great progress supercapacitors have made in terms of electrical characteristics and physical sizes. And when we add that trend to low cost engineering of energy harvesting modules, and low power IC loads, suddenly powering ICs and modules from harvested energy sources becomes practical. So today's outline starts by accepting IoT growth and assuming that growth continues to drive the need for more modules. Now, those modules have an infield cost, which is driven primarily by the battery maintenance and battery recycling figures. We'll discuss how supercapacitors can be used in an energy harvesting application to either supplement or replace the IoT module's battery. And then we'll look at various KAVX supercapacitor families and styles and discuss their operating characteristics relative to those modules and powering loads. And then finally, we close with an example of two different supercapacitors that have been loaded with two different loads, a 100 milliamp and a 50 milliamp load at certain duty cycles. And we'll use those curves to just discuss how a module may be powered. Now, those curves are easily generated. There's many other uh, parameters of those curves that are available, and generally, designers might find those useful in assisting with their design of supercap modules for a particular device. Now, what we're looking at here is a generic IoT block diagram. It's an example of a core processor and periphery functions that are powered by either a battery or an AC power source. Now, the batteries, of course, they could be bulky, they could be costly, they might require maintenance or they will require maintenance. And if alternately you're powering from AC mains, that eliminates the portability of the IoT module and it potentially raises a need for backup power. So, although many modules may be powered in this fashion, it's not an ideal situation for all modules. And of course, the architecture on modules will vary depending upon what's being done and etc. But this is a good general comparison of what would be expected out there. The need for energy harvesting and IoT is pretty easy to recognize. If we looked at maybe looking at strain on the blade of a windmill, it's going to be very hard to replace a battery there. Alternately, we might be looking at a module which is operating on a pier or on a buoy or something like that, or microwave links of air quality. So those being so remote, that's going to have a real need for energy harvesting to reduce the battery issues. So the five main benefits of energy harvesting and IoT might be a lower maintenance, extend battery life, reduce the size requirements for the overall package, an increase in portability, and much better cost effectiveness. If we were to look at the options of how we would power an IoT module with supercapacitors, there's really two things we could do. As we said earlier, we could either aid or try to extend that battery life, or we could replace the battery totally with a supercapacitor. So let's look into some of the details of both of those. If we look at the first situation, aiding that battery, we would aim to have the supercapacitor sized essentially to take the peak power, deliver the peak power to that load, depending upon the load type and size and its power requirements. Now, in doing that, we could say it's possible that less heat would be generated by the battery throughout its life cycles. We could also say that the battery would not see as deep of a discharge, and generally that's going to increase the lifetime of that battery. There'll be a smaller number of recharges needed, assuming it's a rechargeable situation. And we could reduce the battery size. The supercapacitor could be used to deliver the peak power, and choosing the right supercap might allow us to reduce the battery size. And even though we added a supercap, the overall combination would still potentially be smaller than a battery alone. So that's the case of aiding a battery. The case of replacing a battery, um, that is pretty simple as well. Typically, we're going to need a supercap module that will meet the equivalent voltage and energy density of that battery. We'll see a lifetime extension. We'll have an improved design efficiencies potentially. Of course, cost and savings are going to occur, and lower maintenance and replacements are needed. What we have done here is we've taken that IoT, the generic IoT block diagram that we saw further with all the periphery around that processing core, and we've changed the power source to be KAVX supercapacitors. That could either be a single supercap, it might be a module, there may be a PIMIC on the output of that, but essentially that supercap um, storage unit is going to be charged by some energy source. It might be solar, might be wind, micro, hydro, TEG, piezoelectric, something. It's something along that lines. That energy harvesting is going to occur. It's going to go in self to some form of a PIMIC to charge up the supercap, and then we take that power from the supercap and power the IoT module. So this is a good example of a low power um, situation of the load and supercap and being a single unit. But the situation could also be extended to other types of loads. It might be a higher power type of load. It might be an infinite use UPS system or something like that. Basically, what I'm saying is that we'll show later that we could scale up the size of the storage capacitor bank, and that can be used to power things other than an IoT processor. So hopefully we'll find some parallels to other designs here. Now, knowing that we are either replacing or supplementing a battery, it's good to know some of the characteristics and similarities between these two uh, power sources. um, if we could call the supercap a power source, not in the traditional way. But upper right-hand corner, we'll look at the graph showing the energy density of a battery. Compare that to the supercaps. Of course, the batteries are going to beat supercaps on energy density. On a power density point of view, supercaps are going to beat the batteries. That makes sense because supercaps have the ability to both sink a very large current when they're being charged or deliver a very large current when they're being discharged. So there's many different application notes on how to charge a fully discharged supercapacitor because, in theory, they might even destroy a power supply by drawing so much current. It's good to use those application notes to be safe in the charge of supercaps. At any rate, we can explain well the power density advantages of supercaps versus batteries. On the bottom of the right-hand page, we could see a table which talks about supercaps comparing specifically to lithium ions. Um, well, the charge time on the supercap is much faster. Of course, that makes sense because of the high current that we could sink or deliver, and that's why there's a high power density. The charge cycle life for supercaps looks exceptionally active relative to that of a rechargeable battery at approaching or exceeding a million cycles. Cell voltages are acceptable. The specific energies are less than that of a lithium ion. That makes sense, as we've talked about previously. Specific powers, we beat that dramatically of the batteries. And then both the charge temperature range and the discharge temperature range, those both look very attractive for supercaps. Now, on the left side, we're comparing batteries and supercaps in 14 different areas. And what we could say is the batteries are essentially a slow energy storage mean. It's electrochemical. And what we have with supercaps is essentially the fast energy source. And what we can show is a comparison of where supercaps have advantages relative to that of the battery. And temperature range is a really big deal. Charge acceptance is great. The efficiency looks good. Cycle life stability, power density, all of that looks quite good. And even from a cost point of view, when properly sized, they could be very attractive to the designs. Now, in this page, we're looking at two different material sets that supercapacitors can be made from. There is a a propylene carbonate, a PC material system, and there's an acetonitrile. You can see some temperature differences with the PC material system having a broader temperature range. As we approach those high temperatures, we would have to have some derating on the PC uh, co- uh, components, as you would with the acetonitrile. But that's important to note. There are two different material systems. Now, those systems have some different ESR, some different leakage, and certainly different life ranges. Generally speaking, they're relatively similar. Um, we could see that improvements have been made in the ESR of supercapacitors. Improvements have been made to leakage, and the cap ranges are quite attractive in many instances. Um, of course, reliability is a big issue. There's many different papers that have been published about reliability. Generally speaking, every 10 degrees C of temperature reduction in use, or every zero point 0.2 volts of applied voltage relative to the rated voltage of the part, that will double the expected lifetime of the component. Now we'll build on that a little bit in the next slide here. And what I'm showing is the temperature range on the y-axis relative to the MTTF of the component. Um, as you would expect, operating a component at a lower temperature will increase the operational life of that part. The curves, the colored curves, are actually a comparison of rated voltage to applied voltage. So if we're 100% rated to applied, that's the far curve on the left. You could see as we reduce the percent of applied voltage, for instance, 90 or 80 or 70% applied, we improve the MTTF dramatically. So the general statement of the 10 degrees C doubling the life and the zero point 0.2 volt doubling the life is relatively close. Of course, there's predictors and calculations that are possible, but this is a good rule of thumb, the guide. Now, there's four different form factors that could commonly be used. One would be a radial can, another might be radial modules, then custom modules and prismatic cells. Um, Many people are not aware of the prismatic cell. The capacitance can go up to 20 farads. Voltage is attractive. And these devices are ultra thin. They could be less than 1 millimeter, as low as 0.8 millimeters, or they could be 2 millimeters. And that's a very novel thing for supercapacitors to have a low profile and a height sense on a printed circuit board. Of course, they have a larger XY profile. In some cases, that's perfectly acceptable. And there's use cases for all of these different approaches. The radial cans are commonly the more simple part to use in the sense that they could be used in configuring your own power bank. There's a variety of weights and sizes available. They're relatively easy to fit into any portion of a board. Radio modules are likewise quite usable and quite attractive. They, of course, have a higher operating voltage, but in some cases, if you're limited by XY board area, they might have some limitations on end use. Now, custom modules, those actually have a very large capacitance. They tend to be a much higher voltage as well, and therefore they're intended for more of a high power end system, perhaps power holdup or power drives in motors, etc. Now, all of these charts and comparisons, especially the temperature and voltage derating, really reinforce that these parts can be very reliable in end systems. Much longer cycle time, wider operating capability, and they're quite environmentally friendly. This page actually is more of a description of those four types of components than the prior one. The far left column, the SCC, that's the acetyl based part. That part can go up to approximately 3,000 farads. 1 farad can be achieved in something less than a cubic centimeter. And the 3,000 farad part might be about the size of a small soda can. The rated voltages are attractive. Operating temperature range is attractive. Leads have many different configurations. In fact, they could be anything from a snap in to bent leads, or even the stud mount bolt parts on the upper left of that column. And some of the series of automotive qualified parts, AEC Q200 parts, fall within the SCC family. So it's a high reliability part, high volume type part, and well accepted. Now, the next column to the right, the SCM series connected modules, those likewise are acceptable parts. Those devices essentially have two individual SCCs placed in series to increase the voltage. Of course, the capacitance drops, the ESR doubles, but in many cases, having a single component to drop on a board and to be balanced or unbalanced, either passively balanced, actively balanced, or unbalanced should the end users want, those are good options. Operating temperature range is the same. Voltage ranges could commonly be up to 48 volts, up to 500 farads. They're really easy to use. The parts on the left of the second column are essentially a shell, which is backfilled. Those have great moisture ingress resistance. They're used for exceptionally difficult environmental situations. We talked about the buoy type applications, the remote uh, seismic sensors, the remote microwave links, and alarm sensors. That's the type of end applications they might excel in. Now, the Prismacap SCP series, that's the the propylene carbonate, the PC based electrolyte. Those have up to 20 farads of capacitance in them, and that's going to be increasing with time. The temperature range is outstanding. At the high end, the components are derated to 1.1 volts, a common approach used by all. ESRs look very attractive, low leakages, but the real deal about those parts is the zero point 0.8 to 2 millimeter thickness, and they're ultralight, with the smallest parts coming in at less than 2 grams. They're also easy to use because they have the possibility for a connector to receive them. You snap them in, kind of like a battery, by like putting in double A's in a circuit. Custom modules on the far right, we don't really talk about custom modules, but take a second to just touch on it. This is actually a small module, 48 volts at 168 farads. Um, these can be built into much higher voltages, much higher amounts of capacitance. There is active charge and discharge circuitry on them. They might be more typical of Class 8 commercial vehicles, heavy industrial vehicles then, perhaps rails, buses, or UPS power supplies, the infinite charge discharge UPS power supplies on medical or high rail power loads. Now we'll look into each of these just a little bit more detail. This is the SCC series. This is a acetyl part. Cap range 1 farad to 3,000 farads. You can see the temperature range is attractive. They have a low ESR, low leakage, and a high cap. The link to the product series is on the bottom of this slide. Next is that series connected module, the two SCC parts that are essentially put in series. ESR, of course, increases with parts in series. The cap is going to drop, but These are very attractive as a single component that you could just place in, know it's at a particular voltage. Like we said, it could be up to 48 volts. We're showing a very common 5.4 volt, 5 farad part. The SCP parts, the PC material system, well, those range from 3.5 to 20 volts. Depending upon the temperature range, will be at an applied 1.1 to 2.5 volts. The temperature range looks great, negative 55 to 90 degrees C. These are ultralight, like we said, less than 2 grams, low profile, low ESR, and a great leakage. Now we'll look at the last slide here, and this slide really implies that there's a tremendous future use of supercapacitors, and that's really because of the ultra low power microprocessors and MCUs and systems that are coming out, as well as generally lower power loads, at least for miniature portable devices. What we're showing here on the left is a 100 milliamp load at a 90 millisecond on, excuse me, 10 millisecond on, 9 millisecond off pulsed load. On the right, we're showing a 50 milliamp load. Now, this is actually just a discharge curve. The blue curve is showing that we have a 0.5 farad stack. It's been charged to 5 volts, and when we discharge it at a particular duty cycle and load, this is the amount of time we can achieve that voltage level. And likewise, you could see it for the larger 3.5 farad part. Now, on the bottom, we show the table showing a very small stack volume, a very attractive weight, a great hold up time. Now, this has not been run through any type of boost circuitry. So this is actual voltage coming off the cap with the associated load and leakage on the component. There's many more different types of these curves, different voltage ratings, etc., including ones for those large 3000 farad parts and the exceptionally large modules, maybe 48 volts at 165 farads or even larger. So this type of data exists. This type of information is easy to access. There's some calculators for it, and we'd very much like to help work with end designers to size these components for any size load. It could be IoT or larger. That concludes today's talk. I'd like to say thank you for attending. Hope that we get a chance to work with you, whether it be modeling, etc. But thank you again for attending.